In this A3 tutorial, we're going to go through and we're going to look at unbalanced three-phase delta systems. We're going to have a visual idea of what's going on. We'll avoid a lot of the in-depth heavy math, but we will go through and solve some simple calculations using complex numbers. So let's look at a delta system. Here we are here with, we'll call this line A. We've got an impedance connected here, another impedance and another impedance connected in delta because it looks like a triangle, the Greek symbol for delta. And we'll call this for A, B and C, which means that this impedance here is ZAB, this impedance here is ZCA because it runs between the C and the A, and this one here is ZBC. And we'll go through and we'll assign some values here, some form of impedances. We'll pick a resistance of 20 ohms to go here, and B and C we will pick 20 ohms of resistance and we will put in 15 millihenries. And in ZCA we will also put in 20 ohms, but we will also put in 600 microfarads. In another tutorial I've explained how we get 400 volts relative to our 230 for our system here. So between A and B we'll have a voltage of 400 at 30. Between B and C we will have a voltage of 400 at minus 90. And between A and C we will have a voltage of 400 at an angle of minus 210. So that's our basic system, our basic three-phase delta configured system with an unbalanced load. We can therefore go through and find all of our currents. We can work out our currents in our phases, and we can work out our currents in our line. The first thing to do, if we want to figure out what our currents are, is we need to understand what our voltages are and our impedances. The impedances need to be converted into something that we can use. We know that the total impedance is Z is R plus J XL, and we can figure out here as to what these impedances are. So the first thing we need to do is we need to find out what the reactive components is of these. XL equals 2 pi FL, which is 2 pi, it's a 50 hertz system, and our value of inductance is 15 millihenries, 0.015, and that gives us an inductive reactance of 4.71 ohms. XC is 1 over 2 pi FC, which gives us a capacitive reactance of minus 5.31 ohms. Where does the minus come from? That's because it's capacitive. So we now know what our impedances are. We now know that ZAB is a pure resistor, so that has an impedance of 20 at 0. ZBC has an impedance of 20 plus J 4.71, and ZCA has an impedance of 20 ohms of resistance over here minus J 5.31. In order to use these in our calculations we need to convert them to polar form, which we can do. The polar of 20, 4.71 close bracket equals 20.54, 20.55 at an angle we call F of 13 degrees. Similarly, we can do this impedance here with the capacitor. Now, another common mistake for students, getting their signs incorrect. We need to put in that's a negative J, 5.31, which gives us 20.69 at an angle of minus 14.87. So we now have the value of our impedances here and the voltages across them, so we can now work out our currents through them. So the current through IAB is the voltage across IAB, this voltage here, divided by the impedance AB, which is 400 at an angle of 30 divided by 20 at an angle of 0. 400 divided by 20, we don't need our calculator for. That's 20. 30 minus 0, 0. There, it's not 0, it's 30. IBC is the voltage across the impedance BC. And that voltage is 400 at an angle of minus 90 divided by our impedance ZBC, 20.55 at an angle of 13.25. 400 divided by 20.55 is 19.4. Minus 90 minus 13.25 gives us an angle of 103 degrees, minus 103.25. ICA is, so the current through here is the voltage over here divided by its impedance, VCA over ZCA, which is 400 and minus 210 divided by 20.69 at an angle of minus 14.87. 400 divided by 20.69, 19.3 at an angle of, the angle is minus 210 minus 14.8, which gives us an angle of minus 195. Now, we can start plotting some of these in the phasor diagram because things are going to get quite interesting fairly soon. So we'll plot these here for now. We have our applied voltage, VAB, which is up here somewhere. VBC and VCA. We can put in our currents. Our IAB current is 20 at 30. There it is there. Our BC current can be plotted at 19 at minus 103. So this is minus 90 here, 0, that's minus 90. So that current will be down here somewhere, of roughly the same magnitude as this, which we'll plot roughly there. And our ICA current is at minus 195, which will be like this. Now, what's interesting to note here is we see that in the BC phase, the voltage is leading the current, which is not surprising because it's an inductive one here. Similarly, in the CA phase, the current is leading the voltage, and again, that's not surprising because it's a capacitive one. So we've now found the currents that are flowing through each of these loads. The question is now, what's the current that's flowing in our line? Again, we simply can't do a straightforward root 3 translation like some people have done with balanced systems because this is not a balanced system. So our root 3 process, once again, does not apply. If we look at the current flowing here, has got to be the difference between these two currents, because we cannot create current and we cannot magically get rid of it. If we've got a current flowing out of here and out of here, we need a current that's flowing in to provide that. So to find the current in any one of these lines, the expressions or the equations are reasonably simple. It is IA, the current flowing here is the difference between IAB and ICA. The current flowing in line B is the difference between IBC and IAB. And the current flowing in line C is the difference between ICA and IBC. An easy way to remember this is whichever current we're trying to find here, this one here is the same one. So we're trying to find A, so we have AB minus the second one. So there's no BC in here because of the A. To find IA, it's AB minus CA. To find B, BC minus AB. Again, that's what we're trying to do. To find C, it's CA minus BC. So if we want to find B, we need B and B. If we're trying to find A and A. Trying to find C, C and C. That's the easy way of remembering it. We know what these currents are in polar form. In order to subtract that from that, we need to do a rectangular polar conversion to do our subtraction and then convert it back again. And to do all of those straightforward sort of transactions, that's the subject of another tutorial. I'm not going to do it here. But I'll let you go off and do it, or hit the pause button and go and do that, and you can come back and double check your answers, because your answer should come up with 36.3 at an angle of 7.8, 36.2 at an angle of minus 127, and 27.9 at an angle of 120. Now there's some interesting things to note here. The first one is the magnitude of these currents is not the same. The first two, the magnitude's 36, that's pretty close, but this one here is significantly less. And if we plot these over here, we can see this. We can see what the extent of this. 36 at 7.8, well that's 20, so it's going to be roughly twice that length on this sketch, so it's going to be up here somewhere. So that's IA. IB is again 36, so roughly that same length down here, and it's at minus 127. We know that that there is 90, minus 90, 127, that's roughly going to be out here. IB is 36 minus 127. 36 at 7.8. And IC is 27 at minus 120. At 120, sorry, which is up here. Now, you'll notice that, well, some of you would have done calculations and you would have got 27.9 at minus 240. This is a good opportunity to point this out and to say that that answer there and that answer there are the same. We've got the same magnitude. One of them says 120 in it leading, which is like that, and the other one says at 240 lagging, which is like that. So a 120 and a minus 240 are the same because it's all 306 degrees apart. It's all referenced back to our reference point. The only thing is one of those is leading and the other one is lagging around like that. So we've now calculated not just the currents flowing in each of the phases, but we've also calculated the currents flowing in the lines. And you will see that, again, there's no relationship between root 3 and any of this. It simply doesn't apply. We can now go on and calculate the total power in the system. So the power in the system is the real power of each of these things. So we need to find the power in phase AB, for example. Power in AB is the voltage in AB times the current in AB times the cosine of the difference. Magnitude of the voltage is 400. The magnitude of the current is 20, and the angle between the voltage and the current between 30 and 30 is 0. So the cosine of 0. So that answer to that there, the cosine of 0 is 1. So the answer is 400 times 20, 8,000 watts. The power in BC is VBC IBC times the cosine of the angle BC. VBC we've already established is 400 volts. IBC is 19.47. The angle is 13 degrees times the cosine of 13. Where does 13 degrees come from? It's here. We've got the voltage here at minus 90 and the current at minus 103. 103 minus 90 equals 13. And we can see that if we would go through and do that calculation there, the total power in the BC line is 7579 watts. PCA, VCA, ICA times the cosine of the angle of CA, which again is 400, times our current, 19.3, times the cosine of the angle here. If we come up to this one here, we can see that the angle here is 14 degrees. And again, it's the same thing. It's the difference between the current and the voltage. And that gives us a solution of 7474 watts. So the total power in the system, total real power, is that plus that plus that, which is 23,053 watts. The total reactive power, QAB, is exactly the same sort of process. It's VAB times IAB times the sine of that angle. The angle is 0, sine of 0, that comes to 0. QBC, VBC, IBC times the sine of the angle of BC, 400 times 19 times the sine of that angle, and that gives us an answer of 17.85 kVAR. QCA, VCA, ICA times the sine of the angle in CA, and that gives us 19.82 kVAR. Now again, because this is a capacitive, it needs to be the minus. We talked about this up here. So we can find out what the total QT is, the total reactive power in the system, and it is 17.85 plus minus 19.92 minus 2. So, despite the fact that our system has a pure resistance and an inductance, the size of this capacitance and the frequency that the system operates at means our total reactive power is actually, our total system is actually capacitive. If we looked at this in the power factor triangle, total, we would have a real power here of 23053 and a Q of 2. So here is our S, our total S overall, which we can find by saying ST is PT plus, or in this case it's actually minus JQT. Do a polar conversion on that. 23, 2, close bracket, equals of 23 at an angle of 5 degrees.